So we're going to do a sample problem that has to do with equivalent loads and distributed loads. And what we have is a beam. You can consider it floating in space, or maybe it's simply supported or fixed at one end. It really doesn't matter because what we're interested in is this load distribution. So we have a 10 pound point force, 60 degrees off of the beam. We have a 25 pound-foot couple, and we have this distributed load where at one end it's 6 pounds per linear foot, and at the other end it's 4 pounds per linear foot. And we're asked to find the equivalent loading at point A, and then again to find the equivalent loading at point E. So first things first is let's lay out our argument. What are we actually going to do? So the first thing we want to do is we want to convert the distributed load into 2-point loads. So you can see kind of that we have this triangular load and a rectangular load. And we know the area and the centroid of these two shapes, so we can split this one distributed load up into two smaller distributed loads, a triangular load and a rectangular load. And then we know where to locate the equivalent force for these two distributed loads, and we know what the magnitude is. Once we've done that, we want to determine the resultant forces. So the force resultant at A in the x direction, the force resultant at A in the y direction, and the moment resultant at A. And finally, we'll do the same thing, force resultant at E in the x direction, force resultant at E in the y direction, and the moment resultant at E. So this is kind of the steps we're going to end up taking. So let's first try to split up these loads. So I have this 10-pound load coming off at 60 degrees. Well, I can split that up into a horizontal and vertical component. So for the vertical component, I have 10 pounds times sine 60 degrees, and that gives me 8.67 pounds. And for the horizontal component, I have 10 pounds cosine 60 degrees, and that gives me 5 pounds. So this vertical component is 8.67 pounds, and the horizontal component is 5 pounds. I can also split up my rectangular and triangular loads. So for the rectangular load, right, this is 4 pounds per linear foot, and this is my shape. So the force of that rectangular load is 4 pounds per linear foot times the width, which is 4 feet, 16 pounds. And I know the location, it's just the centroid of this rectangular load, which is 2 feet from the edge. The force for my triangular load is this height, which is 6 pounds per linear foot minus 4 pounds per linear foot, so 2 pounds per linear foot, times the length, again it's 4 feet, and since it's a triangle, it's half the area. So I get a force of 4 pounds. So 4 pounds, this one was 16 pounds. And this length is 2/3 times 4 feet. So 8/3 feet. So I've now split up my point load and my triangular load, my rectangular load, into these nice x and y components, and I know where they're all located. So again, this is just the numbers we've calculated from the previous page. And what we're trying to accomplish is I'm trying to say that this system is equivalent to this system. And then again, that this system is equivalent to this system. So to make these systems equivalent, I need to make sure that the force resultant from this upper system produces a force resultant in this lower system. So if I sum the forces in the x direction in this upper system, I get the force resultant that needs to occur in this lower system. So I only have the 5-pound load, so my force resultant in the x direction is 5 pounds. I can do the same thing with the vertical loads. I can replace these 3 vertical loads with one single vertical load force resultant. So my force resultant in the y direction is 8.67 pounds minus 4 pounds minus 16 pounds. So I end up with negative 11.33 pounds. So physically what this means, my force resultant in the x direction is 5 pounds. My force resultant in the y direction is minus 11.33 pounds. So rather than have this upward arrow, I should have an arrow pointing downward with a magnitude of 11.33 pounds. So the net effect of this 5 pounds on this system is to push this system with some force to the right. That's what we're accomplishing down here with this 5 pounds. And similarly, the net effect of these 3 vertical forces is to have some vertical translation, and that's picked up by this 11.33 pound effect. So the last portion of this is the moment. It's the rotation. So if I sum the moments about A in my upper system, I get some moment resultant at A. So using the right-hand rule to be positive, my moment resultant at A is 8.67 pounds times 2 feet. So it's the perpendicular force times the perpendicular distance plus 25 pound-foot couple minus 4 pounds times 5.33 feet minus 16 pounds times 6 feet. And all of this comes out to be negative 75 pound-foot. So what we had done with our force in the y direction, we're going to have to do the same thing with the moment resultant. So the net effect of the moment resultant is a clockwise rotation, or it's trying to cause a clockwise rotation of a magnitude 75 pound-foot. So this system is equivalent to this system down here. So we found an equivalent loading at point A, which accurately represents our original system. So lastly, we're asked to find the equivalent loading at point E. So again, I've redrawn our point loads that we've split up already, and I need to just find the force resultant and the moment resultant at point E. Well, the force resultant in the x direction, the force resultant in the y direction don't change. So we still have 5 pounds to the right. Our force resultant in the y is 11.33 pounds downward. Those haven't changed. What has changed is where we're summing our moments. So now the resultant couple might be different. So we can go through and we can sum the moments about E, and we're going to get some moment resultant at E. So again, using our upper free body diagram, summing the moments about point E, using the right-hand rule, taking that to be positive, I end up with the moment resultant at E is minus 8.67 pounds times 4.62 feet. So the force times the perpendicular distance plus 25 pound-foot plus 4 pounds times 1.29 feet plus 16 pounds times 0.62 feet. So our moment resultant at E ends up being 0. So we have no rotation. And what this is telling us is that the rotation that the original loading was trying to impose, we can represent that effect by placing our force resultants at a specific location. All right.